Today, Dr. Chanel Fortier, who is a research chemist for the USDA ARS in New Orleans, Louisiana at the Southern Regional Research Center, will be talking with us about her research looking at metal ion analysis. This is part of an effort to develop a database going forward, looking at different cottons, different locations, different prototypes, and I'll let her go ahead and give her presentation.
Thank you, Dr. Rogers. So today I'm going to be talking about investigating metal content on cotton lint grown in well-watered and water-limited conditions. So some motivation behind this project. Metals in cotton fiber has been previously studied in the literature. Potassium has been shown to have the highest abundance. Copper and iron have been shown to cause yellowing in denim goods. Magnesium affects dyeing at elevated temperatures. And calcium and magnesium form metal dye complexes which are insoluble, water insoluble. So the objectives of this study were to perform metal analysis on cotton fiber, to investigate the effect of water-limited versus well-watered field conditions, to explore the relationship between metal ions, cotton quality parameters, and cotton varieties, and to develop a database of metal ion content. For this study, we looked at 7 varieties: the Kala 1517-99, the Delta Pine 393, New Mexico 1303, Fibermax 958, MDDC, the PX variety, and the AU variety. The 8 metals we looked at were potassium, calcium, magnesium, sodium, iron and copper, as well as manganese and zinc. The HVI parameters we looked at were micronair strength, upper half mean length, elongation, uniformity, short fiber content, RD, and plus B. Now it's important to note that all of these studies were taking place at Maricopa, Arizona in 2014, and this was done to minimize the effect of growing location. So to start off with our sample prep, we took 0.5 grams of cotton, placed it in a Teflon vessel, and then put on a composite sleeve. Next, we added a 1-to-1 mixture of nitric acid as well as distilled water. We allowed it to sit for a pre-digestion stage for 10 minutes. Next, we put it in the Morris instrument, the microwave accelerated reaction system shown here at the bottom in blue and white. After we digested the samples, we diluted the samples, and then we ran them on the ICP OES. So ICP OES, what is that? So that's the inductively coupled plasma optical emission spectroscopy. One of the good things about this technique is that you can determine multiple metals at one time in standards as well as samples. Compared to atomic absorption spectroscopy, it employs a torch rather than combustion flames, so it's safer to use. Thus, the development of electrically generated flames actually evolved. ICP is a type of plasma source in which the energy is supplied by electric currents, which are produced by electromagnetic induction. ICP OES is capable of quantitative data based on the creation of calibration curves. So now we're going to look at the results. This first table, table 1, is actually showing the 8 metals that I talked about earlier versus the 2 field conditions, which were well-watered and water-limited. Magnesium is highlighted here because according to the least significant differences, the means between the well-watered and the water-limited were statistically different. All of the other metals had significantly, they were very close, the means were very close. So for table 2, we look at the metal ions again, now in the presence of the varieties, the 7 varieties, and the field conditions. And what we see here for the Kala 1517-99 is that there's a statistical difference between the means for the well-watered and the water-limited for the sodium metal. When we look down at MDDC, We also see a statistically different mean between the well-watered and the water-limited field conditions for potassium. For the NM or the New Mexico 1303 variety, we see that for zinc, the zinc metal, that there is a statistical difference between the means there. And for the PX variety, we had 3 actual metals. That included the potassium, the magnesium, and the iron. They all had statistically different means. So a similar graph, but now looking at HVI versus the field conditions, with that we saw the upper half mean length, the uniformity, strength, short fiber content, RD and plus B, they all had statistically different means, whereas the micronair and the elongation did not have significant differences in their means. For table 2, cotton fiber quality parameters were looked at, again in the presence of the variety and the 2 field conditions, the water limited versus the well watered. We see that for the Acala variety, the upper half mean length and the uniformity both have statistically different means. For the Delta Pine 393, we see that for uniformity, again, we see there's a statistical difference in the means. For the FiberMax 958, we see the upper half mean length, uniformity, and RD have shown that they're statistically different in the means. MDDC for micronair, upper half mean length, uniformity, as well as RD, all had statistical differences in the means. The New Mexico 1303, upper half mean length, uniformity, strength, RD, and plus B, all of these HVI parameters showed differences in the means. And then for the final variety, the PX variety, we see uniformity as well as plus B had a statistical difference in the means. So for table 5, we're looking, now we're switching gears, we're looking at correlations now. The correlations between the metals with themselves. And what we found was that for magnesium, there was a strong correlation with sodium, copper, and iron. Sodium and copper had a strong correlation. Copper and iron had a strong correlation. Now for the magnesium, the copper and the iron had negative correlations, as well as the sodium and copper have a negative correlation. So for table 6, we're looking at the correlations of metals with fiber quality parameters. And what we found that was only for zinc that there was a statistical difference, that there was a strong correlation between the elongation and the plus B. So for the correlation among fiber quality parameters only, we see that the upper half mean length, the uniformity index, for the uniformity index and the strength and the short fiber content all had strong correlations. For the uniformity index, we see a strong correlation with the short fiber content. And short fiber content also had a strong correlation with the strength. With the plus B parameter, we see that there's a strong correlation with strength and elongation. So to sum up, the potassium, calcium, and magnesium yielded the highest concentration for all of our studies. Only magnesium showed a statistical difference between the means of the well-watered and the water-limited field conditions. For the average metal concentration as a function of variety, we see that the Acala variety, the MDDC, the New Mexico variety, and the PX variety all show statistical differences in the means of the well-watered and the water-limited field conditions. When observing the effect of the field conditions on fiber quality parameters, only micronair and elongation means were not significantly different. While observing the effect of variety on cotton quality parameters, the uniformity index had the largest amount of varieties with statistically different means, including the Acala variety, the Delta Pine variety, the FiberMax, the MDDC, the New Mexico, and the PX variety. When correlating the metal ions with themselves, magnesium had a strong correlation with sodium, iron, and copper. I'm sorry, sodium, copper, same thing. Sodium, copper, and iron, and the sodium had a strong correlation with copper, and copper had a strong correlation with iron. When correlating the means with the fiber quality parameters, zinc had a strongly negative correlation with the RD and the plus B color parameters. When correlating the fiber quality parameters with themselves, the short fiber content was strongly correlated with the upper half mean length, uniformity, and strength, and the plus B was strongly correlated with elongation and RD. Overall, the effect of varying the field conditions on cotton varieties and metal ion concentrations were determined. So with that, I would like to acknowledge Ashley Willis and Mia Davis for helping out with the sample prep. And in the future, we'd like to look at different locations. The current study, all of the samples were taken from Maricopa, Arizona. We would like to look at different locations and see how that parameter affects the results. And also we want to find out, are the metals on the surface of the cotton, or are they in the cotton fiber itself? And that concludes the presentation. I'll take any questions.